Hello, Professor Sargent, here with you again for another Math 101 flipped classroom session. This is section 4.4, day 2. This question is an extension of things that we are already talking about in the first day. Profit is revenue, the money that comes in, minus cost, the money that goes out. Abbreviate revenue function as R of X and the cost function as C of X. Then we're going to have to subtract. The formula we're given for R of X is 9.27X. And we have to subtract all, so I'm putting parentheses around this, of the cost function 2.95X plus 90. We're going to have to distribute the minus sign. That's going to include changing the sign of the 90 and combine the like terms with the x's. That's going to give us, I believe, 6.32x. So I'm going to erase the rest of this and see if they agree. Double checking here. Yeah, it should be 3.92x minus 90. It's good. And then they ask us, what is the profit if 90 of the t-shirts are sold? If it comes out negative, then that amount is money that's being lost. If it comes out positive, then it is money being earned. Let me bring up the calculator, just a moment. All right, so since we have the formula in part A, instead of having to go back and individually for this value of X, which is 90, instead of having to figure out the revenue and the cost and then subtracting, if we wanted to figure out how much profit would be earned for several different values, we'd rather have that single formula for the profit. I'd be taking 6.32 times 90 and then subtract this 90. That's a different 90 that came from the cost function. And we're coming up with 478.8. Remember, that's a dollar amount. So we should be typing that as 478.80. And MyLab has already put in the dollar sign for us. I'm pretty sure that if we left off the 0 after the 8, that it would mark it wrong. I could be incorrect about that, but I doubt it. Next, what we have to talk about, we've talked about using addition and subtraction to create new functions from old functions. For some reason, it's not included in this section, but you could multiply and divide. You'd have to be careful with division. 0 is a polynomial. Also, you'd have to watch out for what values of x you put into the polynomial so that it doesn't make the polynomial 0. But not only could we add and subtract, we could multiply and divide to create new functions. We're not going to talk about the multiplication and division, at least not yet. On page 307, we're going to talk about something else called the composition of functions. And the idea here is you take the output of one function and use that as the input of a second function. And I kind of set that up in today's class where I'm computing your numerical grade via a variety of formulas. I could put that all together as one thing. Whatever I get, I have to take that output of a numerical grade and then send that to what is your letter grade at the end of the semester going to be. Now, we have this open circle written right here. That's not a multiplication sign. That is a composition sign, which could be read F follows G. Although we're reading left to right, you're seeing G afterwards. If you think about this with order of operations, when we rewrite that and see what's on the right-hand side of the equal sign, G is inside. So put in X into G, get an output, and last Fx on it. So let's see some examples here. Now you may have noticed that they were talking about the range of the inner function and its intersection with the domain of the outer function. When we look at f follows g of 5, the 5 is sent to 9 by g of x, and then 9, when we plug that in to f, is giving us 7. I'm going to erase that in a moment, but I need to point out the following. If we had reversed the order, G follows F of 5. If we had F acting first, then F would send 5 to 8, and then 8 would go to 7. Okay, that matches up, but let's see what else. If we put in 6, F would send 6 to 9, and then G would send 9 to 8. Whereas if we put in 6 into G first, it's going to give us 6, and 6 goes to 9 instead of 8. So the order matters. Also, let's see here. It's about all I can say on that so far. All right, let's take a look at evaluating another, but written a different way. Okay, so this one has a particular value of x. I'm going to write this down on my board back here, let you take a look at that in the meantime. So we're told that f of x equals x squared plus 3. H of x is x plus 7. And we're supposed to evaluate f follows h at -6. All right, here we go. So again, order matters. We're putting -6 into h. H of -6 would be -6 plus 7, which gives us a +1. And I'm going to color code that. Put that in purple here. So that purple 1 is going into f of h of 6. Sorry. We found out h of -6 is +1. So I turn around and put that +1 in for x in the first, the x squared plus 3. Okay, so that's going to be 1 squared plus 3. So 1 plus 3 is going to give us an answer of 4. Let's check that. Make sure they agree with that. Kitty wanted to say hi. She's making a cameo here. Okay, now notice there it had the notation with F, open circle for composition, H, so F follows H. I naturally just written it this way, F of H of -6. And again, let's see if they agree with the answer of 4 on this. And they do. Okay, now let's take a look at coming up with a formula. Now we're given formulas F and G. Notice the order of that. G follows F. So whatever we get from F, we'll turn around and plug that in to G. You can do the same kind of color coding I did with the numbers there. So let's see here. That would be the same as G of F of X. And we don't have a particular value of X. So we're talking about taking that entire formula for F and plugging that in to the formula for G. Wherever we saw X before in the formula for G, it's going to get replaced with an X squared plus 3. So the 4X becomes 4 times the quantity in parentheses, X squared plus 3. And notice it says to simplify the answer. So I multiply, I'll distribute the 4. And it would also be natural to combine the like terms, 12 plus 5. That's part of the simplification that they're expecting. 12 plus 5 is 17. So let's see, once I've got that, if they agree with that answer. And it's good. One more with coming up with formulas in terms of an application, though. Okay, so we're given what is hopefully an obvious statement. F of X equals 60X computes the number of seconds in X minutes. And then the function G of X equals 60X also computes the number of minutes in X hours. What is F follows G of X, and what does it compute? This should verify for us that composition is not the same as multiplication. Remember, F follows G of X. We could write F of G of X. And our formula for G of X was 60X. So what we're doing is we're taking that 60X. When we plug that into F, that is taking the place of the X. So we're not doing 60X times 60X. That would be 3600X squared. What we're getting here is just 3600X. And what that's computing, since G was applied first, we turned the number of hours, X, into the number of minutes. And then we further break down the minutes into seconds. So if we have X hours, multiplying that by 3600 is going to give us how many seconds there are in an hour. So how many seconds in X hours? It only gives us one try on this, by the way. And they agree. There is one more thing to talk about, which is graphing some polynomial functions. Give me a moment here and I'll show something about that. By the way, we already know how to graph lines. We can review that in Wednesday's class. But for the introductory video, I'm going to leave this out and go to graphing some other polynomial functions. Hey, kitty, relax. So here we want to graph f of x equals -2x squared. And before we can do that, we need to know what the most basic polynomial of degree 2, what its graph would look like. So I'm going to first figure out what y equals x squared looks like. The way I'm going to do this is by a table of values. Since we know that any real number squared is non-negative, I'm going to pick positives and negatives and 0. We know 0 squared, 0 times 0 is 0. 1 squared, 1 times 1 is 1. 2 squared, 2 times 2 is 4. And 3 squared, 3 times 3 is 9. So if I were to put -1 in, -1 squared, -1 times a -1, those two negatives are going to cancel out and give me another +1. Same thing goes for plugging in -2, we'll get +4, and plugging in -3, we'll get +9. So let's see what those 7 points look like when plotted, and talk about how we may want to connect those. All right, so on my fancy site here, -3, 9. Yep, didn't get in the parentheses. -3, 9. And let me zoom out. Now let's do it this way. -3, 9. There it is. And then we had -4, 2. Sorry, that was -2, 4. And then -1, 1. 0, 0. And you should notice here that there appears to be some curvature to this. And I could plug in values for x all day long. The domain of y equals x squared is all real numbers. But so that you don't think that, oh, maybe we should have some jagged line segments so that it goes beep, 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 beep. No, it's curved. So what if I put in something in between, such as in between these two, like -3.5 is an extra thing. -3.5 squared. I don't know what that is off the top of my head, except that it's going to be positive. Oh, I should have picked something in between -2 and -3. So let me change that. -2.5 and -2.5 squared. There we go. So we're not connecting this with some line segment. We're going to connect with a curve. Now get the other side of 0, 0. We had 1, 1, 2, 4, and 3, 9. The function that we were talking about was the most basic quadratic function. Quadratic is another name for degree 2. And the type of figure we're going to have is going to be the most basic parabola. Y equals x squared looks like this. The domain of this is all real numbers. The range going from bottom to top, we don't see anything for a while until we hit y equals 0. So our domain in interval notation, parentheses around -infinity to +infinity. And our range starts at y equals 0, and then it keeps on going. On paper, you'll need to show arrows at the ends. Let's see, what else? Now they wanted us to graph y equals -2x squared. So what that's going to do is change the y values. After the y values we just found, it's going to multiply all of those by -2. That should still leave us with a parabola. Same kind of shape. To get it to graph on MyLab, then we're going to press click to enlarge graph and select the parabola shape here. And we could take -3 comma, instead of 9, multiply 9 by -2, it's going to be -3 comma -18. And let's see here. Watch the upper right-hand corner here. -3 comma -18. You watch that upper right-hand corner of the pop-up window before you click, and you can be sure that it's plotted where you want it to. Now it's asking us to plot another point. I had -2 comma 4. 4 was the original y value. I'm multiplying that by -2. So 4 times -2 is -8. I'm going to plot the point -2 comma -8. I'm not sure it took the previous one. Did it? Yeah, it did. Okay. So -2 comma -8. There's that. It's still showing us a line, so it's expecting another point or two at least. So now I go over to the -1 comma 1. 1 times -2 is -2. So I'm going to plot -1, -2. And it seems to have locked things in. So I'm going to press save down here towards the lower right and check my answer. And they agree. So notice what it's done is the negative sign has flipped it over and the 2 has stretched it out vertically compared to what I originally graphed. Let's take a look at another. So now, oh, okay. The domain. All right. So I already said that that would have to be -infinity to +infinity. That is the domain of any polynomial function. And careful there. Make sure you're in that little blue box before you get the infinity. As for the range, because it flipped it over, instead of going square bracket 0 infinity, because it's flipped over, we're starting at -infinity, comma 0 square bracket. And it's good. So I think we just have one more to look at. Let's find it here, just a moment. Well, what if they asked us to graph the polynomial function g of x equals x cubed minus 1? First of all, let's find out what y equals x cubed looks like. So let's see here. Put in -3 and cube it. Now that there are 3 copies with a negative, the first 2 negatives will cancel each other out, but then you're multiplying by another negative. That number is large enough that you're not seeing it show up. So I'm going to zoom out. When doing this on paper, if you're given a grid of a certain size, then you're going to have to pick carefully what your scale in the x and y direction are. If I put in -2, -2 cubed is going to be -8, and -1 cubed is going to be -1. 0 cubed is 0. 1 cubed is 1. 2 cubed is positive 8. And 3 cubed is 27. By the way, both with the parabola and with this, I am using some symmetry. There was symmetry with respect to the y-axis for the parabola. The y-axis gave us something being split into mirror images, whereas here, the origin is acting as a point mirror. There is origin symmetry to this. So when I connect, hopefully that's even clearer on this, that we're going to be connecting with a curve. So here's the graph of y equals x cubed. Same thing, you'd have arrows at either end. Both the domain and range would be all real numbers. So your domain and your range for a degree 3 or cubic function, which gives you this shape kind of like an S. I call it a snake climbing up a wall. The domain and range would be negative infinity to positive infinity. So if I'm going to then graph g of x equals x cubed minus 1, my claim is that that's going to take all the original y values and push them down 1 unit. It's a little hard to see it right now. Let me zoom back in. Every single one of the original points is now 1 unit lower than it was before. The green was the original. And now we're seeing in blue what happens when we subtract 1 from the original y value. For example, we see that negative 1 comma 1 on the original. That has moved down to negative 1 comma negative 2 on the graph of f of x equals x cubed minus 1, or g of x, whatever you want to call it. Similarly, the negative 3 comma negative 27 that we had way down here this thing is so steep that I have to zoom in a bit to be able to tell the difference. Here's our negative 1 comma negative 27 on the original. And I want to look at one lower than that, negative 1 comma negative 28 on the graph of g of x. Oh, sorry, negative 3. Negative 3 comma negative 28. And if I zero in on that target and zoom in, we should see the original in green show up a little more clearly. And then our new point, negative 3 comma negative 28, showing up on the blue. And we do. All right, that's all I've got for now. Hope that helps, and I'll see you in class soon. Stay safe and healthy.